Welcome back, everybody. So the objective, we were on series techniques of investigating if a series is convergent, divergent. So series. So quick review. 11.3 to 11.8. Quick review. We learned that we define a function that we call a sequence. A sequence is a function an f of n with domain and natural numbers. And then we say that, hey, we have the terms of the sequence, a sub 1, a sub 2, a sub 3, and so on. We're interested in understanding the behavior of a sequence while n goes to infinity. So we're interested in finding the limit of an while n approaches infinity. Remember that we said, hey, this type of function is not very interesting for us. As a mathematician, we're interested in creating some new objects. We're going to take the terms of this function and create a series. So sequence and series. By taking the terms of previous function, a sub 3, a sub 4, we create a series. The sum n starts from 1 to infinity. And we say that, okay, now that we create a new object, we're interested in coming up with something that help us to check to see if this new object is convergent or divergent. Well, we said that we construct and form the partial sums. Using S sub n, which is a1 plus a2 plus a3 plus a sub n, which is itself a sequence. So S1 is a1, S2 is a1 plus a2, S3 a1 plus a2 plus a3, and . So we say that if this sequence is convergent, we say that this series is convergent. If Sn is convergent, so we say that our series sigma an is convergent. So as you can see, we go back and forth using the technique that we learned in convergent, divergent sequences to work with a series. But we saw that, hey, sometimes it's hard for us to analyze a series. Some series are easy to recognize. For example, if we have a geometric series, a geometric series. For a geometric series, remember that you have a plus ar squared plus ... If r, absolute value of r, is less than 1, we have a convergent series, and it is convergent to the a divided by 1 minus r to this fraction. After geometric series, we introduced some series that the middle terms, they are opposite of each other. We can get rid of the middle terms, and we call it telescopic series. Okay, then we said that, what is the next step? What if we have a series that doesn't satisfy the definition of a geometric series or a telescopic series? Then we said that if a function, general term, satisfies 3 conditions, we can use integral test. And then using integral test, we introduce P series. series 1 over n to the p, n starts from 1, goes to infinity. Then we also said that we can use the known series to help us compare complicated series, comparison tests. Then after introducing comparison test, we talked about limit comparison test. Limit comparison test. In limit comparison test, we have the limit of an divided by bn while n approaches infinity equal to c. If c is greater than 0, then both series are convergent or both of them are divergent. Okay, do we have more tests? There are some more tests that we're going to talk about today. One of them is called alternating series. Very well. Sometimes you see this series that we call alternating series. The behavior of this series is like this. Definition of alternating series. Okay, if you have a series like sum of -1 raised to n minus 1 times bn, n starts from 1, goes to infinity. This series is called an alternating series. So why is that? Because if you plug in different values for n, we get this. We have -1 raised to 0, b sub 1, plus -1 raised to the first power, b sub 2, plus -1 raised to the second power, b sub 3, and the rest of the terms. So it's going to be b1 minus b2 plus b3 plus the rest of the terms. This series is called alternating series. So I expect you to ask, now that you're introducing a new series, when does this series convergent? This series is convergent if it satisfies these conditions. First of all, bn is greater than equals to bn plus 1. What's the meaning of that? It means that this guy is decreasing. And second of all, if you take its limit, the limit is 0. Alternating series, the sum -1 raised to n minus 1 times bn. This is called alternating series. In general, we don't say that this series is convergent. If it satisfies these two conditions, then it's a convergent series. The term bn is decreasing and its limit is 0. For example, give us an example. This is too abstract. Analyze this series. -1 raised to n minus 1 divided by n. N starts from 1, goes to infinity. Okay, take a look at this. Is it geometric? Is it telescopic? Integral test? P-series? Comparison test? Limit comparison test? Which one it is? This is a new series, alternating series. So if we want to list some of the terms, it's going to be -1 to the power 0 divided by 1, plus -1 raised to 1, which is -1 over 2, plus then -1 raised to 2, a third, minus a 4, plus the rest of the terms. Alternating series. So is it convergent? Is it divergent? Remember that when you're analyzing your series, always remember to do the first step. Step 1, the limit of the general term must be equal to 0. Always check this condition. Sometimes you're lucky and that guy is not equal to 0, and you can just at the beginning say, hey, the series is not convergent. So since this is equal to 0, we can move on to the next step. Step 2, check the convergence of this series. What do we have to check? We have to check 1 and 2. 1 says, well, Bn must be greater than equals to Bn plus 1. It must be decreasing. Remember that to check this guy is decreasing, we can always take the derivative. F of n is 1 over n, or just Bn is 1 over n. The derivative Bn prime is -1 over n squared. As you can see, it is negative. The derivative is negative. It means that Bn is decreasing. Two, we need to check the limit to the limit of Bn while n approaches infinity. We already know about the behavior of this sequence, 1 over n, while n approaches infinity, which is 0. So the second condition is met. So the alternating series is convergent. There you go. Give us another example. We want to feel more comfortable about these types of series. Okay, let us start analyzing this guy here. Question says, analyze this series. The series, it has -1 raised to n, okay. And we have 3n, 3 times n. On the denominator, we have 4n minus 1. And then n starts from 1, goes to infinity. Okay. So first of all, we might say, hey, the exponent here is n, but the exponent here is n minus 1. Very well. So how do we convert this guy into n minus 1? If I start this series from the second term, I can convert this guy from n minus 1. So we have this conversion that this guy is equal to. We can write it as the sum -1 raised to n minus 1. So wherever you see n, you can just substitute that by n minus 1, divide by 4 times n minus 1 minus 1. And now your n starts from 2, goes to infinity. If you compare these two series, they give you the exact same terms. N is equal to 1, so you get negative 3 divided by 3 or negative 1. If you plug in 2 here, you get negative 1 times 3 divided by 3, which is negative 1 again. So what I did, I added 1 to my first step, n equals to 1. Now n is equal to 2, and subtract 1 from each of these n's to make the exponent the same as the exponent that I have here. So I can rewrite this guy as series n starts from 2 to infinity, negative 1 to n minus 1. And here I have 3 times n minus 1. I'm going to leave it as it is, divided by 4n minus 4 minus 1 of 4n minus 5. Okay, very well. So now I have an alternating series, and this guy is my Bn. Negative 1 raised to n minus 1, and my Bn is here. Okay. So if you find the limit, does the limit goes to 0? Does the limit of negative 1, remember this is a step 1, negative 1 to n minus 1, 3 times n minus 1 over 4n minus 5 as n approaches infinity. Is it 0? What do you think? So on the n terms, this guy is either negative 1 or positive 1. So you either have plus or minus. But what is the limit of 3n minus 1 divided by 4n minus 5? These two have the same exact exponent, 1 and 1. It means that it is 3 divided by 4. So it's equal to either plus or minus 3 over 4, which is not equal to 0. So step 1 is not met. We cannot go to step 2. There you go. Another definition for you. The definition of absolutely convergent series. So let's write down the alternating series as well here. Definition of absolutely convergent series. A series, this new object, the sum an, is called absolutely convergent if absolute value of the terms, general terms, you form the series is convergent. The series, like sigma an, is called absolutely convergent if the series of absolute value of its terms is convergent. If not, we call it conditionally convergent. There you go. We have a theorem. Our theorem says if a series is absolutely convergent, then it is convergent. Okay. So when you're dealing with series that has negative signs, you don't have to work with them. You can work with the absolute value of the terms. It means you can get rid of the negative terms and only check the series with positive terms. For example, question says, analyze this series, sum -1 to n minus 5 divided by n squared, n starts from 1 to infinity. For this series, you have two options. The first one, it's similar to an alternating series. Option 1 is following the definition of alternating series. Check those conditions. Or check to see if it is absolutely convergent or not. Option 2. Absolutely convergent or not. Okay, let us check both of them. You see the result is the same. Alternating series, yes, of course, it's an alternating series. If I take the limit in step 1, so step 1 for both of them are the same. So step 1, the limit of -1 raised to n minus 1 divided by n squared while n approaches infinity. This is a number on the numerator. This is a scalar on the numerator divided by infinity, which is 0. So we have the permission to go to the next step, step 2. Check to see if this series is convergent or not. Very well. So remember, as an alternating series, the first condition was Bn is decreasing. Bn is 1 divided by n squared. So Bn prime is equal to, let me see, -2 divided by n to the third, which is negative on its domain. Because n is positive, your denominator is always positive, your numerator is a negative number, so this guy, the whole fraction is negative, decreasing. And the second step is to show that the limit of Bn while n approaches infinity is 0. So you have the limit of 1 over n squared, n goes to infinity, which is 0. So the first condition is met, second condition is met. The alternating series, it says, hey, this guy here is a convergent series. What if we use absolutely convergent? Theorem says if a series is absolutely convergent, then for sure you can say that your series is a convergent series. Okay, absolutely convergent. It means that first we have to create the sum of absolute value of this guy here. -1 to n minus 1 divided by n squared. N starts from 1 and goes to infinity. Okay. On your numerator, you have -1 with different exponents. It means that it oscillates between -1, positive, -1, positive, -1, positive 1. Its absolute value is always 1. So this guy is equal to the series 1 divided by the absolute value of n squared. N squared is always positive. The absolute value of positive numbers or positive terms is equal to those numbers or those terms. There is no change. And start from 1 to infinity. Okay, what is this series? This is the P series. P is larger than 1, so it is convergent, which is a 2 series and convergent. The theorem says, since this series is absolutely convergent, it is convergent itself. Since this series is absolutely convergent, it is convergent itself. Okay, we have 2 more tests before we finish up the techniques, the tests that we're using for series. Okay, root test and ratio test. So let us write ratio test. Ratio test says if the limit of absolute value of a sub n plus 1 divided by a sub n as n approaches infinity is equal to L. If this L is less than 1, so if you take the limit and that limit is equal to L and that L is less than 1, then you say that your series is absolutely convergent, so it is convergent. Then the series is absolutely convergent, so it is convergent. If the limit is larger than 1, then the series is divergent. Is divergent. The third case is if L is equal to 1. In this case, this test doesn't work for the series. The test does not work. It means that we have to use other methods, other techniques. So this is your ratio test. Let's add that. You have a root test as well. Root test. So root test says if the limit of now nth root of absolute value of an as n approaches infinity is equal to L, we have the exact same scenarios. If L is less than 1, then the series is absolutely convergent, so it is convergent. If it is greater than 1, it is divergent. If it is equal to 1, the test doesn't work. ratio test and root test. Okay, give us an example. So just write down this example for you. It says, hey, start analyzing this series. Example, okay, series -1 to the n, and third, and 3 to the n. Okay, and starts from 1, goes to infinity. Very well. What we can do, we can just form the limit of absolute value of a sub n plus 1 divided by a sub n and find that limit. If you're that lucky to get L, the number less than 1, and for sure we have a series that is convergent. Don't forget your step 1. Step 1 is that the limit of -1 to the n to the third, 3 to the n, as n approaches infinity, you need to check that limit first. So this guy is just a number, positive -1. This guy is n to the third, and on the denominator you have an exponential term. The denominator goes to infinity much faster than n to the third. So it is already a scalar divided by infinity or 0. So step 1 is met. So we can go to the next step. Step 2. Step 2. Since we learned a new technique, let us apply that. Let us use the ratio test. The ratio test says, hey, find the limit of absolute value a sub n plus 1. It means that wherever you see n, you need to replace that by n plus 1. So you have -1 raised to n plus 1, n plus 1 to the third, divided by 3 to n plus 1. This is your numerator, divided by your denominator, which is an itself. We copy down an, which is -1 to n to the third, 3 to the n goes to infinity. Okay, perfect. So what do we have here? First of all, since we are taking absolute value, we're not worried about this negatives. So we can just ignore the -1 to power, any power. This guy simplifies to limit of absolute value. We need to multiply the first numerator and the last denominator. So this guy is our new numerator. Here we have 3 to the n times n plus 1 to the third divided by, and we multiply the first denominator and the second numerator, and this is n to the third times 3 to the n plus 1. Our job is to find this limit. Before finding this limit, we can simplify this more. Let me erase this part of the board. We're not using these tests anymore. This is equal to the limit of absolute value of 3 to the n plus 1 to the third, divided by 3 to the n times 3, n to the third, n goes to infinity. So as you can see, we can cancel out 3 to the n, 3 to the n. What's left? 1 over 3 is left. So you have 1 over 3 times the limit of absolute value of n plus 1 to the third divided by n to the third, n goes to infinity. But this limit is equal to 1. This is just, so we get L to be a third. L is less than 1. It means that the series is absolutely convergent. So convergent. Let me write this note here for you. The limits of an x to the n plus the rest of the terms divided by bm x to the m plus the rest of the terms is equal to am a sub m a sub n divided by b sub m if and only if n is equal to n. So n goes to infinity. So while n goes to infinity, we don't care about the terms with lower exponents. We just care about the terms with the maximum exponent, the leading terms. And if n is equal to m, you can ignore these two, and you're left with a sub n divided by b sub m. In our case here, you have n to the third, n to the third. Limit of n plus 1 to the third, n to the third, as n goes to infinity. This is n to the third plus the rest of the terms over n to the third as n goes to infinity, which is equal to. That's how we get 1 here. Perfect. Very well. Give us another example. Okay. Let's go over one example. I'm going to give you a little bit challenge here. So if we see a types of series like this, what is our approach? Okay, perfect. So this example says find or analyze the series n to the n, okay, divided by n factorial. N starts from 1, goes to infinity. Remember n factorial is 1 times 2 times 3, to n. And when it comes to n plus 1 factorial, this is just n plus 1 times n factorial. For example, n plus 2 factorial is n plus 2 times n plus 1 factorial. We can also write down n plus 2 factorial as n plus 2 times n plus 1 times n factorial, and we can continue this process. Very well. Okay. N to the n divided by n factorial. Let us use the technique that we just learned today. We're going to construct the limit of absolute value of an plus 1 divided by an as n approaches infinity. Okay, this is the limit of, on my numerator, wherever I see n, I replace that by n plus 1. So I have n plus 1 raised to n plus 1 divided by n plus 1 factorial. Everything is divided by an, which is n to the n, over n factorial. I want to find this limit as n goes to infinity. Very well. Okay. So I'm going to multiply these two, then multiply these two, and and rewrite the limit so I can simplify it eventually. This is the limit. A bit skewed. So you have the limit of absolute value of n plus 1 to n plus 1 times n factorial divided by n plus 1 factorial times n to the n as n approaches infinity. Now our job is to simplify this as much as we can. So this is the limit of absolute value n plus 1 to power n plus 1. This is n plus 1 to power n times n plus 1 times n factorial divided by n to the n stays the same, and you have n plus 1 factorial, which is n plus 1 times n factorial as n approaches infinity. Very well. I can simplify this as n factorial, and n factorial cancel out, n plus 1 and n plus 1 cancel out. What's left? The limit of n plus 1 to power n divided by n to the n as n goes to infinity. Remember that n values are all positive, so we can get rid of absolute value. You don't need the absolute value anymore. All terms are positive. Very well. You saw this guy in Math 1A. This is the limit of n plus 1 divided by n to the power n while n approaches infinity, which is the limit of 1 plus 1 over n to the power n as n approaches infinity. So this guy is just equal to Napier number. Okay, so now that we have the Napier number, this is from Math 1A, it is a Napier number. Okay, E, of course it is greater than 1. Since it is larger than 1, this is L, and larger than 1. So the series is divergent.